All right, we're going to define and we're going to compare and contrast physical properties and chemical properties. So we're going to make a column for each and just draw a line down the middle to separate the two and put a few bullets um, about both physical properties and chemical properties. And of course, a property is just a quality or characteristic of something, not a property as in ownership, but a quality or characteristic. And the first key idea that I want to make underneath physical properties is they can be observed without changing composition. So physical properties are observed or determined. So you can observe a physical property like color, you can determine a physical property like density, but you can always do that without, and I'm going to write W/out as an abbreviation, without composition change. And the Greek letter delta is going to be representing change here. That triangle is a nice bit of shorthand that we use a lot in science to talk about change. So physical properties are observed or determined without composition changes in the substance. So you can measure the density of something without changing its composition. Therefore, or related to that is the fact that physical properties depend only on the substance itself. And what I mean by that is it does not depend on a reaction with anything else. Depend only on the substance itself. Let's put some examples down here, and then we'll talk about chemical properties. So, a example that I gave before was density. That can certainly be determined without changing the composition of the substance. Color. If I gave you an aluminum cube and asked you to calculate its density and observe its color, it's still made of aluminum. The composition of a substance, what I mean by that is its chemical formula, right? Its makeup can always be described with chemical formula. Other examples might be conductivity, and that could perhaps refer to the conductivity of heat or the conductivity in terms of electricity. And then finally, we're going to include all phase changes like melting point all phase change determinations like melting point, boiling point, and so on. So those are examples of physical properties. Chemical properties, by contrast, are ones that can describe the potential for composition change. And why do I say describe the potential for composition change instead of just saying describe composition change? Well, because a chemical property may be that something does react or it may be that something doesn't react. So they describe the potential for composition change. And in parentheses, I'm going to write IE. Think of that as, in effect, chemical change. So we're talking about the possibility or the potential for chemical change when we talk about a chemical property. Like flammability is an example of a chemical property because some things are flammable and some things are not. We're talking about the potential for it to change composition in that kind of a reaction. For that reason, chemical properties depend on reaction with other substances. And this is an abbreviation for with. A W with a slash. Sometimes taking notes, it's very helpful to have a couple of bits of shorthand that you can use. And examples would be things like reactivity of all sorts of different types of reactivity. I could list reactivity with acid, reactivity with water, reactivity with oxygen. Other examples include flammability, corrosiveness. But one that we're going to pay particular attention to is pH. So I'm going to put an asterisk here because we're going to continue in a moment to discuss pH as an important chemical property. So I'll pause here for a minute before moving on to discussing pH. And a good question to consider before moving on might be whether solubility is a chemical or physical property. So it'd be a good time to pause the video and try to base your discussion off of these bullets. Is solubility, for instance, the ability of salt to dissolve in water, a chemical property or a physical property of salt? The final point that I want to make about chemical versus physical properties is that pH is a really important chemical property. It's an important chemical property because it describes a substance's acidity or alkalinity. Now you could argue that by telling me a substance's acidity, you have also told me its alkalinity. In other words, its basicity, because if something is very acidic, then it's not very basic, and vice versa. So alkalinity is synonymous with basicity. And this is a spectrum going from acidic on one end to basic on the other. And so I'm going to make a compare and contrast chart here. And we'll describe acids versus bases. I'm going to just make a short line here to divide two columns, and right on that line I'm going to put the number 7. And that's because 7 corresponds to a neutral solution, which is neither acidic nor basic. So we're going to count down from 7. 6, 5, 4, 3, 2, 1, and write those numbers in the acidic range, and up from 7, 8, 9, 10, 11, 12, 13, 14. Anything with a pH of 11, 12, 13 would be considered very basic. A pH of 8 or 9, mildly basic, and so on. So this is the pH scale, and we should be at least this familiar with it at this point. Now, pH is going to have to wait until we have a better understanding of some aspects of chemistry we won't discuss just yet, but we should include a couple of bullet points underneath acids and bases for now. First of all, we've defined pH as a chemical property which describes a substance's acidity. And that really could be thought of as a reactivity with water. How does an acid react with water? So under this left-hand column, I'm going to put a bullet that explains that acids react with water to form what we call hydronium ions. And a hydronium ion has chemical formula H3O+, and they're also known as hydrogen ions. So I'm going to write AKA hydrogen ions, H+. So we won't be able to understand this concept just yet until we've defined what an ion is a little bit more carefully, but acids react with water. So pH is really about a chemical property. And there are a few other ways to define acids, but this is the way we're going to start learning about acids. Called the Arrhenius definition of an acid. How it reacts with water is it forms hydronium ions. We're going to contrast that with a base. Bases react with water to form a different type of ion called hydroxide. Bases react with water to form hydroxide ions. And the formula of a hydroxide ion is OH-. And there's no other way that hydroxide ions are known, unlike hydronium. Sometimes people say hydronium, sometimes people say hydrogen, and they're really referring to the same phenomenon or species. And it might make sense that if we take hydronium and hydroxide, we get water. H+ and OH- makes water. So this is why we think of acids and bases reacting together to neutralize each other. but some of that chemistry can wait until later in the year. Finally, it's helpful to remember that acids tend to taste sour. So, for instance, vitamin C or citric acid or ascorbic acid is vitamin C. In lemons, those are going to taste sour. And bases tend to taste bitter. Things like soap or baking soda are examples of basic substances. So that's as much as we need to know about pH for now. Know the pH scale. Know that really pH describes reactivity with water, and a few examples of each couldn't hurt.